Okay, it appears that we are all set to go. Once again, thank you for joining this morning or this afternoon, wherever you may be. My name is John Cusimano. I am with Exida, and the webinar you've tuned into is called The 7 Things Every Plant Manager Should Know About Control System Security. Of course, you don't need to be a plant manager to participate in this presentation, but this information is good general information for anybody involved in control system security. As I said, my name is John Cusimano. I'm the Director of Security Solutions for Exida. I have over 20 years of experience in the field of industrial automation, starting with as a control system engineer for Eastman Kodak Company, and then working for 2 different manufacturers, More Products Company and Siemens, where my focus of my work there was with control system reliability, safety, and security. I have a couple certifications. One is Certified Functional Safety Expert, and the other is Certified Information System Security Professional. I'm involved in several different industry associations, all related to control system safety and security. The ISA 99 Committee for Security, the ISA 84 Committee for Safety, and the ISA Security Compliance Institute, and the Department of Homeland Security's ICSJWG. A little bit about Exida. Exida is a company whose focus is helping our clients improve the safety, security, and availability of their automation systems. And as you can see, we have offices located around the world where we serve our clients. So for today's agenda, we have 3 main topics. First, I'll start with a brief introduction into control system security, just to make sure everyone on the call is grounded in some basic terminology. And then I'll move on to the 7 things that every automation professional should know about control system security. And if time permits, I will go into describe a project case study of a control system security assessment performed in late last year. And I can, a little bit of forewarning, I did the session this morning. We did run a little over. The case study takes a little bit longer, so if you need to leave when the time is up, feel free to do so, of course. But I will continue and go through the case study. So what is control system security? Just to make sure we're all clear on the same definition, control system security is all about the prevention of intentional or unintentional interference with the proper operation of industrial control systems through any kind of electronic means. That would be computers, networks, operating systems, applications, and so on. It's important to note that it is both intentional and unintentional interference, and I'll explain a little bit more why that's important. It goes by many different names. You may see things called SCADA security, PCN security, industrial automation control system security, industrial network security. We're generally all talking about the same thing, and that is, again, the prevention of any kind of unwanted interference with the proper operation of a control system through electronic or cyber means. It's obviously very important today, and control systems in particular have become more vulnerable today than ever before, for a number of different reasons. First is, over the last 15 to 20 years, we've seen rapid inclusion of commercial off-the-shelf technology into our control systems. For very good reason. Using this commercial technology has enabled numerous features that were previously unavailable through enclosed proprietary systems. So integration of technology such as Microsoft Windows and SQL and TCP/IP networking has not only improved ease of use, but also improved the ability to interoperability between systems, and the ability to move data throughout a system. But unfortunately, with this commercial technology also came vulnerabilities. So now our control systems are subject to the same viruses, worms, trojans, malware that affect IT systems. We also enjoy increased connectivity, being able to integrate our control systems with each other and with business information systems, and even at enterprise level. Again, great advantages and benefits have come from this, but we have also created additional vulnerabilities and pathways into our control systems that didn't exist in the past. Also, demand for remote access. This technology enables us to be able to work anywhere at any time and be able to access our systems remotely. Again, with that comes a lot of convenience and cost savings, but also opens up vulnerabilities. And lastly, information about control systems is publicly available. Manuals, including information such as default passwords, readily show up and are available on the internet. So all of these factors have combined to create a scenario that has made control systems more vulnerable than they were in the past. This slide illustrates some information about actual incident types. It was provided by the Security Incidents Organization, which maintains a repository of industrial security incidents that has been collecting industrial control system security incidents for over 10 years. And in looking at that data, we see some interesting trends. First, of all the incidents recorded in this database, about 80% of them are unintentional or non-deliberate, whereas the other 20% are intentional. The intentional incidents are the ones that we tend to read about and hear about in newspapers and magazines. These sensational stories of hackers breaking into control systems or disgruntled employees deliberately causing problems with a system. These incidents are real, they really happen, and they really cause downtime, loss of production, and even in some cases have caused accidents, including harm to individuals and processes. The other 80% are often do not make the news or the headlines, but nevertheless these incidents cause the same types of problems. They can cause lost production, lost staff time, and even equipment damage and injury and harm. These break down into three categories. There are the insiders, which are generally the case of employees, well-intentioned employees that manage to act on the system beyond their authorization, or just do something accidentally. An example of that might be the IT department technician doing a network scan of a process control system network. The other categories, outsiders, are malware. That is, malware, viruses, worms, trojans that get into the system, not deliberately, but through any number of means, but nevertheless cause some significant problems in plants. There were numerous examples back in 2003 of the slammer worm getting into production facilities, and some major automotive manufacturers suffered tremendous downtime through that slammer worm, for example. The other category that's not often heard about or recognized is what we would categorize as equipment failure or bugs in the system. So network devices or software that untested software that may cause things like network storms or malformed packets to appear on the network can really cause some significant problems with industrial automation equipment. No control system security presentation these days would be complete without having something on Stuxnet, and so I do have a few slides on Stuxnet, but I do want to say this: the focus of this presentation is not on Stuxnet, but on how the things that that users should do to protect their systems from any kind of control system incidents, whether they are deliberate attacks like Stuxnet or accidental or any of the other types that we talked about. But to make sure that everyone is aware of what Stuxnet is and the seriousness of the situation, I did want to put a few slides and talk about it a little bit. Stuxnet is particularly significant because it was the first malware that we are aware of that was specifically targeting industrial control systems. We have seen malware in control systems many times, but we had never seen a virus that was specifically written to attack vulnerabilities in a control system, particularly one that was able to not only access the workstations and servers in a control system, but actually get into the controllers, and designed to deliberately sabotage an industrial process. It was first discovered in June of 2010. However, it was later discovered that it had actually been in circulation since about June of 2009. It has this remarkable ability to be able to reprogram Siemens PLCs, two different brands, and it affects the Siemens. It starts by getting onto a Windows PC that is running the Siemens Somatic software. And once it gets a foothold there, it is able to then communicate directly to the controller. And it does so in a manner that is undetectable. So if technicians are seeing a problem with the system, unfortunately the way the virus works is it hides itself and its actions in a way that it makes it very difficult to troubleshoot. So it then uses the Somatic software to read the PLC memory, look for very specific conditions, and if it finds those conditions, it will overwrite the function block with its own code. And as I mentioned before, that code is hidden from view from the engineering console. It has a very strong capability to be able to spread through numerous mechanisms. It spreads via USB, memory sticks, over local networks, using file shares and print spoolers, and is able to attach itself to the Somatic Step 7 project files and then transfer from project file to project file. It's been reported by some of the antivirus vendors that thousands of PCs have been infected worldwide, predominantly in India, Iran, and Indonesia. Fortunately, for most of those infections, they're benign, because if you are not running the Siemens Somatic software, the infection does nothing more than try to replicate itself or propagate, but does not do any damage to the system itself. Even if it does find the Somatic software, then there has to be a Siemens Somatic controller attached. And again, even in that case, fortunately, the way this was written, it was very pinpointed and targeted, and so only the application it was looking for will be impacted. Nevertheless, Siemens reports there have been approximately 22 cases where it was actually infected systems running the Somatic software. As I mentioned, it has the ability to propagate through the system. The expected entry point into most systems would be through the USB drive. But once on an infected machine, it then has the ability to transfer, as I said before, over local area network using multiple zero-day vulnerabilities that existed at the time. In fact, the mechanism to load itself off the USB drive also used a zero-day vulnerability. Unfortunately, there's been some very good information published in terms of how to mitigate the virus if you have it, to detect it and mitigate it. Of course, one very important source of that information would be directly off the Siemens support website. You can also get different patches from both Siemens and from Microsoft. The table I'm showing now, provided courtesy of the folks at Tofino Security, is a very nice summary of the different mitigations available and organized by the Windows operating system that you may be running, because some of the patches are only available for certain versions of Windows operating systems. For example, the mitigation technique does vary depending on the Windows operating system you're running. So if you have not seen this, you can go download a copy of that from Tofino Security at Stuxnet Central. So that's what I wanted to present about Stuxnet. There's a ton of information available on the internet if you need any more information about that, and of course feel free to contact us afterwards if you need any assistance. What I wanted to get into next is the meat of the presentation, which is what I call the 7 things that every plant manager or automation professional should know and should do to secure their facility from any kind of unwanted cyber intrusion, whether it be Stuxnet or the next Stuxnet or a disgruntled employee or a hacker or any other type of cyber threat. And basically this list of 7 things is really, it's a distillation from a number of different sources, from different standards, best practices, and guidance documents out there. What you'll find if you're new to this field is that there is a lot of information. The subject of control system security has been very active and been studied by security researchers and others since the early 2000s. So with that comes a lot of information, but unfortunately it can be quite overwhelming at first when you start diving into this field. And so the purpose of this presentation is to try to help remove some of that complexity and boil down some of the best practice guidance and standards into 7 basic steps. And certainly with any one of these topics, we could talk for hours or more on any one of these topics. We don't have time for that today, of course. So the objective is to provide a high-level overview of these key 7 topics, and then feel free to contact us or do your own research to learn more. So the 7 things that we here at Exida have identified as critical for addressing control system security. First, assess the existing systems. Number 2, document policies and procedures. Number 3, train your personnel and your contractors. Number 4, segment your control system network. Number 5, control access to the system. Number 6, harden the components of the system. And number 7, monitor and maintain system security. Now I'll go through each one of these with a few slides to give you some more background on what we mean. So starting with assess existing systems. If you're a professional in the world of control system safety or control system design or even alarm management design, you should be very familiar with the concept of a life cycle model. Actually, life cycle models are used in a lot of different disciplines. So there is a life cycle model for control system security. And like most life cycle models, it starts with an assessment phase. That is basically taking stock of the current situation, understanding the risks, and understanding any gaps that exist between the system as it is today and where you would like it to be. So that's our point number 1, is to assess existing systems. So we recommend performing control system security assessments of your existing control systems systems, plants, and even at the corporate level. Compare your current control system design, architecture, policies, practices, etc. to the relevant standards, regulations, and best practices. And the purpose here then is to identify gaps and provide recommendations for closure. There's a number of ways these assessments can be performed. They can be performed using internal staff, or they can be performed with a third-party consultant, or a combination of the two. We would definitely recommend that a cross-disciplinary team be put together, involving people both familiar with control systems, IT, and IT security, in order to provide that broad level of knowledge needed to be able to perform such an assessment. It's also important that the assessment team be neutral, so not involved with the manufacturer of the control systems, not involved with the supply of security appliances or security tools and products, and not involved with the design and operation of the day-to-day operation of the control system. And that's to make sure that you're getting a good, unbiased assessment of the current system and any gaps. So the benefit of performing one of these is to provide management with a really solid understanding of the current situation and any gaps, and help define a path forward. These really help to identify and prioritize investments. Most companies do not have a big budget for control system security upgrades. So if you're going to embark on a program, it's very important to identify which are the most significant gaps and where should you invest your money to get the most return on that investment. And it really becomes a first step in developing an overall security management program for the facility. There's some things that anybody performing an assessment needs to be very familiar with, a number of different standards and best practice guidance documents. So I've identified several different relevant standards and regulations and guidelines in the next couple slides. One of the most important ones, we feel, for anybody working in the field of control system, industrial control system security, is the ISA's 99 series of standards. This work has been going on for almost a decade. And the ISA 99 effort is the result of literally hundreds of individuals that are members of this Standards and Practices Committee working together to define these standards and best practices. It's not a single document, so it's actually a series of documents, 3 of which have been published, but a remainder of work still is yet to be completed. So it's a work in progress, but several key sections have been published and are available now as both ANSI ISA standards as well as IEC standards. So the IEC 62443 series of standards is or will be the equivalent to the ISA 99. And as I said, a few documents have been published, most notably ISA 990201, which is also 62443 IEC-2, which is a standard for establishing a control system security program for end users. A very important document if you are an automation end user to be familiar with. Another important standard, particularly if you work on federal systems, is the NIST standards. National Institute of Standards and Technology, SP 882, is basically the U.S. government's guide to industrial control system security. NIST and ISA have enjoyed a strong cooperation, so a lot of the information from the NIST standards has been integrated into the ISA standards as well. There are other industry-specific standards you should be aware of if you're working in any of these particular industries: petroleum, chemical, electric power, actually chemical again. The API has a SCADA security standard. The American Chemistry Council publishes guidance on addressing cybersecurity. NERC, or the North American Electric Reliability Corporation, has a series of standards that are actually mandated by law in the U.S. By FERC. This applies to the electric entities providing power to the electric bulk grid in the U.S. And lastly, the Department of Homeland Security has also regulations impacting chemical facilities, the Chemical Facility Anti-Terrorism Standards. Part of that is the risk-based performance standards, and although they cover a number of different security issues outside of cyber, RBPS 8 is dedicated to cyber. And this is not meant to be a complete list. There are other standards. There are some national standards, and there are some standards and guidance documents for other industries as well. Lastly, in this area of assessments, I wanted to point out, if you're not aware, you should visit the Department of Homeland Security's Control System Security Programs website. There you'll find information on a number of very good topics. One is published vulnerabilities, and specific to control systems is available here through the ICS cert. There's also information on training, additional recommended practices, and information on some self-assessment tools that are available to help supplement your work in performing assessments. Moving on, topic number 2 in the 7 things is document policies and procedures. It's very important that the company or the enterprise document their specific policies and procedures around control system security. Most organizations do have IT security standards, but I would caution you not to apply those directly to your control systems. There's good information in those, and they should be looked at and perhaps modified to apply to the control system environment. But the requirements around availability and confidentiality and integrity for control systems are quite different than they are in the IT environment. So it's important that and precedence has been set in most major companies to have a separate set of standards for control system security, usually developed through a joint team working between IT security and control system department. Things that need to be addressed in these policies are things like remote access. Are you going to allow remote access? How are you going to allow remote access? To what types of employees and for what reason? Are you going to allow contractors to have remote access? Again, how are you going to do that? With what type of secure mechanism and with what type of criteria and authentication of these users? What are your policies around portable media? We just learned that that Stuxnet spread through USB drives. So some companies, upon learning that, immediately banned the use of USB drives in their facilities. And that seems like a reasonable response to take. The problem with that is that you still have the need to move data and to move files between machines. And so if you're not going to allow portable media, how is that going to be accomplished? You wouldn't want to ban portable media but then have people plugging in their laptops that could be just as easily infected and actually much harder to detect. So it's important to have solid programs in place in terms of what you will and what you will not allow. And we'll talk more about portable media and security of portable media a little bit later. In fact, we'll talk about all these topics, patch management, antivirus management. throughout this presentation, the point on this particular slide is that as an organization, it's important for you to determine what your policies are and to document those. Number 3 then follows quite nicely after number 2. So if number 2 is that you document your policies and procedures, number 3 then is to train your personnel, your contractors, and your visitors on what are your company policies and procedures, and make sure that people are aware of the dangers of control system security. We're all used to seeing safety campaigns throughout our facilities. We're not used to seeing security campaigns, but lack of security can lead to safety incidents. So it's important that we also make sure personnel are aware of the importance of security and aware of and have been trained on policies and procedures. Training really needs to vary depending on the role of the person. So we would recommend role-based training. Starting with visitors and contractors coming into the gate when they first get their security training, they should also be getting some, or their safety training, they should also be getting some security training. For example, if you have a policy that says that contractors are not allowed to plug in USB drives that they bring in, you need to make sure that they're aware of that from the moment they walk through the front gate. And enforce that by making sure that they're not, for example, carrying these devices. New hires, operations, engineering, maintenance, management, all need to be trained, and they all need to be trained in different ways. So we recommend role-based or tiered training depending on the role of the person. So our first 3 topics are what I would kind of call soft topics. We did not get into any technology issues. These are personnel policy type issues. Number 4, though, does, and number 4 is a very important topic, which is segmenting the network, designing a defense in-depth strategy into your control system network. And by that we mean borrowing from the IT world, which has long been compartmentalizing networks. We need to partition our control system networks into distinct, what we call security zones. And the next few slides will help illustrate this concept. But the idea of zones is to group together assets that share common security requirements. And there can be zones within zones and subzones, and zones can be physical or logical or both. The key thing is to define the security objectives and the strategy for each zone, and then create secure means to communicate from zone to zone. We call those conduits. So this is a key concept from the ISA 99 series of standards, this concept of zones and conduits. And this illustration comes right from ISA 9901, showing kind of a generic system architecture here with the enterprise level, and then 3 different plants that are networked together. And each plant has an office network, and then each off of that office network then is the control system network. So one possible and rather intuitive method of partitioning this into zones would be to define one zone for the enterprise level, 3 different zones for each of the plants, and then subzones for each of the plant control systems. This concept can also be extended to more distributed systems like SCADA systems. So here you see, again, an enterprise level, a zone for the control centers, and then zones for each of the remote sites. Now, there are a lot of different models or reference models for zoning systems, and there's not necessarily any right or wrong answer, but there certainly is best practice. This diagram here shows a kind of a generic model for breaking down all the way from the outside, from the internet, down through multiple layers, the corporate management boundary, the enterprise network, then the plant information system. And then even breaking down within the plant, there may be different operating units that should also be considered separate zones because they do not necessarily share the same security requirements. And then within each operating area, a supervisory zone, a control zone, and worthy of note here is a dedicated zone for safety, or safety systems. Also shown here is wireless and remote access zones. Now most major control system suppliers publish a reference architecture for their systems to help users understand how to apply zones to their systems. So for example, Honeywell publishes their reference architecture as shown here, which is basically a 4-layer model. Emerson for the Delta V system publishes their reference architecture. Siemens publishes a reference architecture, and you'll notice most other vendors do as well. There's a lot of similarity between these designs, the basic concept being the control system being one of the lowest layers in the model, and usually there would be some kind of a demilitarized zone, DMZ, sitting between the control system and the enterprise or the business network. Also, many end users have developed their own reference architectures. One well-known one is the DuPont reference architecture. DuPont reference architecture also is a 4-layer type of architecture with the business or the office network and the control system network separated by something called the operation management zone. This also could be referred to as the demilitarized zone. The purpose here is to make sure that systems in the business on the business network do not have direct access to the control system network. They have to request their information through a server in the operation management zone, and likewise control system components cannot talk directly to the business network. They have to communicate through the DMZ. And then also notable here is the dedicated zone or subzone for the safety system within the process control zone. Item number 5 in our list of 7 things is control access to the system, or said differently, manage access control. It's very important to control and monitor who has access to the system, to what resources, with what privileges, and how is access control going to be enforced. And by access control, we are referring not only to logical login to a system, for example, but also physical. Who has physical access to control system resources? Is the equipment room where the PLC and DCS racks, is that open to anybody in the plant, or is it restricted access? Same with the control room. Operators need to have access to the control room, but we also need to secure that access. There's 3 main aspects of access control. There's the administration of that, there's the authentication, and the authorization. Authorization starts with policy. What's the company policy around access control, and who will be given permission to access information? Authentication is proving the identity of the person, and there are many ways this is done. Single-factor authentication with passwords, dual-factor authentication using things like tokens or smart cards, and even things like biometrics. And then the administration of access control, which can be very cumbersome and very difficult thing for companies to manage, particularly as systems grow large. So it's very important that you have a plan around how access control is going to be administrated before you start installing equipment. And then in systems that are broken into multiple zones, you have to look at access control on a zone-by-zone basis. There's two main types of access control. There's access control, the simple access control matrix, which would basically be a simple matrix saying who has access to what resources. There's also something called role-based access control, whereby users are assigned to roles, and then each role has an assigned set of rights. How you decide to go about this really depends on the size and the complexity of your system. But it is very important that you address the concept of access control within your system and really have the ability to identify, again, who has access with what privileges and with what rights. Topic number 6, Harden Control System Components. A system is made up of components, and any single component can be the weak link in the chain. So it's very important that you harden the different components of the system. And by harden, we mean several different things. One is to remove or disable any unused communication ports. The components in our control systems today consist of workstations, servers, switches, routers, firewalls, PLCs, lots of devices with communication ports, particularly Ethernet ports or USB ports. And most of these devices have more ports available than we are using. So it's very important to remove or disable any unused communication ports. There's a lot of different ways that can be accomplished. It can be accomplished through actually physically removing them, as I've seen done in some cases, by physically disabling them. Like I've seen cases where companies have injected epoxy into USB ports so they can't be used. Or other tools, some physical devices as well as software-based tools to disable via software. Again, there's no right or wrong answer, but you have to look at, in your individual case, how effective these controls are, how difficult they may be to bypass, and what's the likelihood that somebody might attempt to bypass. I'll give some examples in a moment. Another is to remove unnecessary applications and service. This particularly applies to workstations and servers and flexible devices that where you can install various different softwares and applications. You really want to make sure that your, particularly your Windows workstations and servers, are only running the absolute necessary applications and services, and everything else is removed. Most control system manufacturers provide good guidance, and even will provide hardened boxes or provide a set of rules. And if those aren't available, NIST also publishes hardening settings. Apply patches when and where possible. Patch management's a very difficult subject in the world of control systems. We don't have the luxury of installing patches and resetting systems like we do in the office environment. And we also can't afford the risk of applying a patch and finding out that it doesn't work or it causes a problem with the system. So patch management, and I have some slides coming up on some best practices around patch management. But it is important that when a vendor releases a patch for that applies to your control system, that they be evaluated and they be deployed if possible. Another thing is to consider whitelisting tools. Whitelisting tools are applications that kind of the contrary to antivirus or blacklisting, enforces this rules around what software and applications are allowed to be installed on the platform and disallow everything else. And lastly, consider using security certified products. As I said, I have a little bit more information on some of these hardening topics. One is to make you aware of some devices available for port locking that we found in some of the projects we've done that provide the ability to both block unused ports and require a tool to remove those, and also lock cables into patch panels and switches so that they cannot be accidentally removed. So this is one alternative. As I said, there are many different ways to handle the topic of unused ports. But this is one that several of our clients have found to be pretty effective and provides a very good deterrent from accidental or deliberate removal or insertion of unauthorized devices. I said patch management is a difficult topic for sure in the area of control system security. In fact, there's a entire working group in ISA 99 devoted to the topic of patch management, and they're making some good progress on defining some best practices. One of the best practices that we've run across in our work is this idea of having machines identified as either early adopters or no-touch machines, and perhaps different levels in between. Early adopter machines are those that can receive patches as soon as available, and they also act as a platform for testing and quality assurance of patches. Whereas no-touch machines are those machines that are so critical to the operation that you really must have manual intervention before you install a patch, perhaps maybe only on a turnaround, for example. But as I said before, it's very important when a new vulnerability is announced or a patch or fix is available that you need to have a team available to evaluate the potential impact on the control system. That team could include your vendor, in fact should include your vendor of your control system. But in order to make an informed decision, you really need to evaluate the potential impact on the control system. And then you can evaluate whether or not that patch will be installed and what the timing would be, if it's going to be installed right away or if it can wait for the next maintenance cycle. Talked a little bit about application whitelisting already. As I said, unlike antivirus solutions that rely on blacklists to block, whitelisting only allows a small list of applications to run on the computer, and everything else is blocked. So whitelisting is generally easier to maintain and has less performance impact on systems. We are starting to see control systems start to adopt whitelisting type applications. So again, I'd recommend working with your control system supplier to learn details on what they recommend. And the last thing in this section on hardening would be, as I said, consider using security certified products. As mentioned before, the weakest link in the system can bring down the whole system. And so there's a new program available from the ISA Security Compliance Institute. It was introduced in late 2010 called ISA Secure. And ISA Secure is a product or an embedded device security certification program that looks at three main aspects of a control system product. It looks at its how the software was developed by the manufacturer, the manufacturer's software development life cycle, particularly from a security standpoint. Do they follow good secure coding practices? Are they testing for security? Are they designing for security? The functional security assessment also is looking at features and functions in the control system product. How does the product handle, for example, access control? How are passwords stored? How are they communicated? Are they stored? Are they encrypted, or are they sent in clear text over the network? Just a few examples of the types of things that are looked at in a functional security assessment. And then lastly, communication robustness testing is testing the resiliency of the device to deliberate attacks on the communications using special test tools such as the Achilles platform that sends network storms and malformed packets and other communications that are deliberately designed to try to impact the network stack, the ability of the device to maintain communications both upward to other devices in the system, but also its ability to maintain control of the process. So moving on to the last topic, item number 7 on the list of 7 things: monitor and maintain. So once you've got your control system, it's been assessed, you've got your policies and procedures in place and people trained, and you've secured, segmented the network, and you've got proper access control in place, and you've hardened the system. Now you need to monitor and maintain. And this is an ongoing job. Unfortunately, in the world of security, we can never really rest because the threats change on a daily basis. A number of different things here. One is to, of course, install vendor-recommended antivirus and update signatures regularly. You need to review system logs periodically to look for unusual events. That can be pretty cumbersome, so there are some products available on the market, intrusion detection and host intrusion prevention systems that can automatically monitor network traffic and have signatures to be able to identify events that may be attacks on the system. Another topic for monitor and maintain would be testing. Penetration testing is something we see done often in the IT security world. Pen testing has to be performed obviously very carefully in a control system environment. You can't penetration test an online system, or if you're going to do so, you have to be extremely careful. So we would never recommend pen testing on a live system, but you can pen test an offline system for perhaps, for example, at a factory acceptance test or site acceptance test, or even in kind of in a lab type environment. And lastly, perform periodic assessments. As I said, unfortunately in the world of security we can never rest, so it's not sufficient to do a one-time assessment and then rest comfortably. You have to keep on top of the security of your control system. I mentioned earlier that Stuxnet is most definitely not the first piece of malware to infect industrial control systems. In fact, in looking through the data of the repository of industrial security incidents, viruses, trojans, worms make up the largest type of incidents that are seen. So we need to make sure our systems are protected from these types from malware. Because malware can result in a lot of problems: performance degradation of the system, loss of system availability, capture, modification, deletion of data, and unfortunately, since the arrival of Stuxnet, we've also seen the ability to actually lose control of the process. So that wraps up the 7 things. And as I mentioned, this unfortunately is a pretty high-level, broad brush overview of these topics. Any one of these could be dived into in a lot more detail, but I wanted to at least present this information. As I said, we are very interested in any follow-up questions that you may have, or if you want to learn more about this topic, please contact us. I also did mention at the start that I anticipated finishing this section on time, but I do have a case study an actual investigation we did of a DCS virus infection, the investigation of that, and the response both by the company impacted. So for those of you who are interested and have another half an hour, or well, 20 minutes or so, please, I will go through the remainder of this presentation and cover this case study. And for those of you who need to depart, of course, feel free to do so. These slides, so I'll say this now, these slides will be available on the Exida website. We also put them on a website called SlideShare. You should be able to find them by searching for Exida and security. And we will also have a recording of this webcast on the Exida website as well. So for those of you who are staying, thank you very much. And as I said, I wanted to go through, thanks to the company that was impacted by this incident. They did give us permission to put together a case study and present that. We presented it for the first time at a Department of Homeland Security conference in the fall of 2010. So the company has allowed us and approved these slides. The only thing that they've asked is that their name be withheld. So this company did experience a pretty significant cybersecurity incident in December of 2009. Company is a petrochemical company complex in South Africa, and it was the control system for one of the units at the front end of this complex that was impacted. Had the unit shut down, it would have shut down the entire complex. Fortunately, in this case, they were able to prevent any loss of production, but nevertheless, they experienced a very difficult 8 to 12 hours of trying to rebuild the system while running the process. They experienced a virus called the Sality virus. It got into the DCS system. Very specifically got into 2 OPC servers that were pretty critical to the communication throughout the system. I will show you in a minute the system architecture, but the OPC servers were providing communications between the DCS and an electrical control system and the DCS and a safety system. So when these servers shut down, the operators were forced to run the plant partially blind for about 8 hours while the engineers were rebuilding the servers from scratch. The virus did so much damage to the servers they were not able to reboot them or even just reinstall the applications. They had to rebuild the servers from scratch. As I said, they were fortunate in that they were able to recover without any loss of production, but it was a harrowing experience for those involved. This is a simplified diagram of the control system network. Brand names of components have been, of course, removed, but I'll give you a quick orientation to the system. At the high level here, these switches here are switches on the plant business network. There are 3 different access layer switches that had interfaces to the control system. This system here is the electrical control system from one vendor. This included servers and comm servers in connection to a lot of different SCADA equipment in the operating most of the motors in the facility. This large system here in the middle is the DCS system, and that was from a different supplier. It was a quite large DCS system with 11 different controllers, many different operator stations, an engineering server, an asset management server, alarm management server, historian. That was interfaced to a safety system from a third supplier. Again, in this case, interfaced through OPC, as well as the OPC interface with the electrical. And then lastly, a vibration monitoring system from a fourth supplier. So all of this was integrated into their overall control system. As I mentioned, the virus was the Sally virus. It had been around for some time, and antivirus programs had signatures for it at the time of the incident. Unfortunately, the antivirus on the DCS system did not detect it. The brand and the update level of the antivirus on the DCS system did not detect it. It was detected on the vibration monitoring system. So actually, going back to this earlier slide, I forgot to put in a build here to show you specifically where the infection entered the system, to the two OPC servers and the vibration monitoring PC. The response from the end user was quite swift. After they got things back under control, they conducted a root cause investigation, and they implemented some immediate policy and procedural changes. First off, they implemented a configuration management policy for the IT switches, for the access layer switches. Those switches were managed by a third-party IT outsourced department, and there was not strong configuration management policy around those. They had VLANs and access control lists that were maintained by this third-party IT organization, but the configuration management policy around that was quite weak. They implemented third-party software policy having to do with who is allowed to install third-party software on any component in the system. They implemented an antivirus management policy. One thing they had found was that even though they were running some antivirus in some components of the system, it was not consistent, and it was not well maintained. They did immediately prohibit any remote access to the system, and they implemented a portable media policy, particularly around USB drives. In this particular case, this facility did continue to allow the use of USB drives, but through very controlled means. Only specific drives were allowed. They were stored in physically secure area that needed to be signed out, and then they had special machines for scanning the media before and after each use. At that point, then they hired a third-party subject matter expert. In this case, it was Exida, to perform a thorough control system security assessment. They were looking for a company that was familiar with DCS, safety systems, SCADA systems, knowledgeable of the latest control system and IT standards and technology, experience in similar plants, and can provide an unbiased opinion. So Exida was hired to perform this assessment. Was done so in August of 2010. And one notable thing is that we followed the relatively new at that time, the ANSI ISA 990201 standard. This is the first of many projects that we have done following this particular this standard. And at the end of this, I will talk about some of the lessons learned around using that and applying that standard to this to control system security assessments. We have a methodology we follow, and again, augmented by the use of the 99 standard. basic, at a high level, the process is to first understand and scope the system under assessment, develop a clear understanding of the network architecture and traffic flows, who is talking to what and what information is being sent, develop an inventory of all network control devices within the boundary of the system, and then basically go visit each device and perform a device level assessment. And that involves a lot of different things, but primarily is an information gathering exercise. We are trying to learn while on site as much as we can about the configuration of these devices, both from a communication standpoint as well as the configuration of the device itself. We interview key employees involved in operations and security of control networks and equipment to understand really what the policies and procedures are. We then analyze that collected data and compare that with corporate standards, regulations, best practices. So in this case, since it was an ISA 99 assessment, we compared our findings with ISA 99. And then at the end of the assessment, before we leave site, we meet with the management and other key stakeholders in the system and describe our findings and recommend solutions to close any identified gaps. And of course, that's followed up with a written report addressing each item in ISA 99, each requirement, why it's important, what the industry best practices are around each of these requirements, what we observed at that site, and our recommendations for closing any gaps. In this particular study, we found we made 48 different recommendations, 9 of which we deemed as critical. So I'm going to highlight some of those observations, not obviously all of them, but some of the key areas that we noted. Number one was network segmentation. There were definitely some significant problems in the way the system architecture, network architecture. A lot of network connections were simply not well documented. There was not good separation between the business LAN and the control system LAN. As I mentioned before, only VLANs and access control lists in commercial switches, which are not sufficiently secure mechanisms. Boundaries were unclear. There were no boundary devices in place. Several computers that we investigated were found to have established hundreds of network connections, both to computers on-site as well as to computers off-site. And we found many instances of dual-zoned or dual-homed servers bridging between different security zones, which is not considered to be good practice. So I said weak boundary, computers with access to literally hundreds of other computers, and many instances of dual-home servers. We decided, working with the client, to apply the DuPont reference architecture to their system, and so this is the result of zoning their system into basically 3 main zones: a business zone, a demilitarized zone, and a process control zone. And each of these zones have subzones. In the case of the process control zone, we broke it into a DCS zone, an electrical zone, a safety system zone, and a vibration zone. And there are boundary devices between protecting each of these conduits. In the demilitarized zone, a portion of the electrical system and a portion of the process control system ended up in the demilitarized zone, and these were the servers that provide the function of passing data from the business network to either the electrical system or from the business network to the process control system. And again, these boundary devices, there are boundary devices in place on these communications, as well as from the demilitarized zone into the business zone. In this particular case, because of geography and where these switches were located, we proposed 3 different firewalls. This could easily also be accomplished with one firewall from the DMZ to the business network. Another notable thing is the OPC firewalls. We recommended OPC aware firewalls, that is, with the ability to do deep packet inspection of the actual OPC communications. And a few other notable things with this assessment. When we looked at system hardening, we found a number of different problems. Workstations had extensive number of inappropriate applications running. Things like VNC for remote desktoping, internet applications and email applications, even games and remote access software, and numerous file shares were configured between devices, which we recommend are removed. We also did, sorry, waiting for the next slide to load. There were a lot of unused ports of it that were not physically secured and with general access. So we made some recommendations around blocking those ports. In this case, because the switches were unmanaged, they could not use management services to turn off unused ports, so they did use physical devices. They had been using blocking USB ports by disabling them in the registry, but unfortunately that's very easily overridden, so they, in addition to that, went to also using a physical device for USB locking. There, of course, were a lot of other findings in this assessment. These are just some of the highlights. So to wrap this up, the lessons learned here, the client, both the client and exida learned quite a bit from this project. The client learned about the importance of good network segmentation, about following their supplier's antivirus recommendations, about how to manage portable media, about awareness and training programs that should be put in place, and how to harden their systems. As an assessor, as I said, this was the first time we had applied the ANSI ISA 99 standards, and did find that it provided very good structure, but notably cannot be used necessarily as a checklist. It provides good guidance, but there are intentionally areas that are not covered by the standard, different technologies, so you need to augment it with additional information and, of course, good experience. Zone and conduit modeling from ISA 99 also worked quite well when applied to this project, both from for the ease of understanding for the client and being able to put a model in place that they could then go deploy. Suppliers' reference architectures do need to be adjusted for real applications. This system, like many systems out there, are not made up of components from just one supplier. So reference architectures are just that. They're for reference, but they do need to be modified for real-world applications. And of course, data collection has to be performed very carefully when working on a live control system. This is something we are very familiar with, but you do need to be cautioned that security, particularly IT security consultants that work in office environments may not be as sensitive to the importance of being very careful when working on a live control system. So the next steps here is the client is developing corporate policies and procedures. They're preparing to deploy the recommended network changes. In fact, at this point, I believe they have deployed those. They have rolled out a training program They are looking at some monitoring technology such as IDS and HIPS. They have done a thorough review of their access control policies and procedures and authentication mechanisms. They have hardened the components of the system with support from their supplier, and they are in the process of investigating or assessing additional units and sites within the company. So in conclusion here, to wrap up, and I appreciate again those of you who stayed the extra 20 minutes to hear about the case study. Hopefully some takeaways for you today is that security is a key component in control system reliability and safety. You really can't have safety and reliability without security. And unfortunately, the threats to control system security are real and are becoming more sophisticated. Fortunately, there are excellent standards, best practices that have been around for some time and have been proven to be able to provide protection. They can't be guaranteed to provide protection against any threat. There's no such thing as 100% security. But starting by applying these standards and best practices will go a long way in making your systems more secure and also make it easier for you to maintain. So as new threats and vulnerabilities are discovered, if you have a good system in place, you'll be able to respond more quickly. Automation equipment suppliers play a major role in making sure systems are secure. Ultimately, it's the responsibility of the owner and operator of the control system to make sure that their systems are secure, but the suppliers of that equipment play a very important role. And it's important to demand security from your automation suppliers. And lastly, assessment is the first step. In order to understand where you are, you need to know how to get to where you want to be. You need to understand where you are and any gaps that exist. So we highly recommend, if you have not done an assessment of your systems, that would be your first step. So again, thank you very much for attending today's webinar. There is a Q&A panel. If you want to send in any questions, I'd be happy to answer those. You also, please feel free to email me afterwards. I did send out an email reminder for those of you that registered, so you should have my email address. It's jcusimano@exida.com. So if you think of any questions later or you want to follow up on any of the topics presented here, please feel free to contact me, and we can have a more detailed discussion.